So we will start off with a little bit of a theory and then we will move on to our previous topic, linear regression. Okay.
Okay.
Whenever we are talking about machine learning models, we will be talking about these terms a lot, and to make clear about these things, so we should discuss it earlier. Now we know dependent variable. Sometime in some books, in some theory, they call it target variable or label variable or output variable. So these are all the same things. So if you go around with any of this, there's no need to be confused about it. Okay. And for independent variables, in some books or in some texts, they just call them features and they don't mention them as independent variables. So if we're talking about features, predictors, or input variables, these are basically the thing that we are talking about as independent variables. So basically, there are dependent variables are the variable that we're going to predict or we are going to find the relationship about, and independent variables are the features are the variables that are basically influencing the dependent variable. And basically we are using these variables to predict that particular variable that we are talking about or we're calling dependent variable. Okay. The next terms that we should understand are training data and testing data. And so whenever we talk about machine learning model, we basically train a model. Now, what is a model? A model is a mathematical formula or something like that. So in the linear regression formula, we know that this is particular formula that we are going to model. Okay. So this mathematical expression behind any model is basically known as mathematical model. Okay. Now, whenever we're talking about training some model, it means we are trying to find the optimum beta naught, beta 1, beta 2, and all these. Okay. By saying optimum, it means that whenever we have this set of values, our line should be close to all the points in the case of linear regression. But for different machine learning models, we will have different constants like these, and we will model different equations like these. Now, what is the training data and what is the testing data? Now, we train a model on a training data. Like if we have a data, we will split it into two, training data and testing data. And based on that, what we will do is we train our model on the training data and we will see that how well our model works on the testing data. Now, the main difference between these two is in the training data, model knows both dependent and independent variable. The model have access to both of these. Okay. And based on that, it tries to create a relationship between these two. Once it's done, it had a trained model, then we can use it on the testing data to see how our model is performing. Do you have any question?
No.
Okay. Now, the thing is, we are going to generate some predictions whenever we are trying to assess the performance of our model. We'll generate some predictions, and based on those, we will talk about how well our model is working. When we're talking about machine learning, we will have two types of model: supervised machine learning and unsupervised machine learning. Now, what is supervised machine learning? So basically, supervised machine learning is when we have a clear question in mind that what we are trying to do here. Okay, we have labeled data. Labeled data means we have clean columns with appropriate names, and we know that this particular column is our dependent variable, and these are our independent variable, and we're trying to find out the relationship between them. Got it? That's what we
Yes.
call supervised machine learning. And in supervised machine learning, we deal with two main groups of problems: the regression problem and the classification problem. When we're talking about the regression problems, it means our dependent variable or target variable is a continuous variable. Okay. For example, it can be price, weight, or something like that. Okay. So basically, it's a continuous variable, and when we are talking about classification problems, it means our main are we are going to predict the different classes. Like for example, if someone send us an email, it goes through Google's model and it label it as a spam or not spam based on that, right? If we feed an image to a model and it gives us two outputs, either it's a cat or a dog, It's basically a classification problem. Like if we are trying to predict the COVID-19, let's say, we just give the symptoms of our patient, and based on that, our machine learning model will tell us that either it's the patient got a disease or not. Okay, so this is basically the main difference between classification and regression. No, whenever we're talking about supervised machine learning, we have a clear problem in mind. We know what is dependent variable, what are independent variables, are the variables that are influencing our dependent variable. And in that we have two kind of problem regression and classification. We discussed them. Are we clear about that?
Okay.
No. Whenever we're talking about supervised machine learning, we will deal with these different models most of the time. Linear regression that we will discuss today, logistic regression model, decision trees, random forest, k nearest neighbors, and neural networks. And in this course, we will discuss all of them in quite detailed and in how that we can perform that on multiple different data sets. After that, we have unsupervised machine learning. In unsupervised machine learning, main goal is to find the patterns that can help us to discover something new or something meaningful. Okay. And here we don't have a labeled data, like we don't know what is our dependent variable. We are just trying to use some variables to find the results without knowing what actually we have, what we actually we're trying to find. Like we don't have any dependent variable or target variables here. Okay. Now, if we talk about what kind of machine learning models we will have here, we will deal with clustering problems. Like we have a data, and based on that data, we want to group three groups or four groups. Now, whenever we're trying to create groups, we basically don't know how many groups there will be. Okay, so it will be totally dependent on us that how many groups we want, and we will create the cluster based on that. And here we have association rule, or a priori, that basically is an algorithm that is used to model the different products or something like that based on like how they get sold in stores. Okay. And the association rule, the main prime example of association rule is the a priori algorithm that I think you studied in your courses as well, and we will discuss it here as well. Basically, we try to find the atoms that get sold in any kind of stores frequently and together, and based on that we create the rules. And like these particular atoms are selling on the every single order or on the similar order style, so we will group them in the store or something like that. The third thing that we can use unsupervised machine learning is dimensionality reduction. Suppose we have a data set with 10,000 columns, and we want to learn some machine learning models and generate some predictions. But the problem is the 10,000 columns are quite a lot to handle, and there comes the dimensionality reduction. So basically, we reduce the number of columns from 10,000 to three or four columns, and these columns also contain the effect of all those columns. Okay, so that's what we call dimensionality reduction. For this dimensionality reduction, we have algorithms like principal component analysis or linear discriminant analysis, LDA. We will discuss them when we are working on them. Okay, so if we are trying to talk about something related to clustering, we go with k-mean clustering, Ritchel clustering. We are talking about association rule, we go with a priori algorithm. And if we're talking about dimensionality reduction, we will basically talk about principal component analysis. Now, this was the basic introduction of unsupervised machine learning, supervised machine learning, and the fundamental terms and concepts. Do you have any question related to any of these?
No, I don't have.
Okay,
Yes.
perfect. Okay, we will continue from here in the next session. We will talk more about the theory. We will talk more about on different data sets, and we will deal with it in Python. Okay.
Okay, thank you.
Okay. Bye bye.
Bye.
Can you see my screen? Okay. Okay. So in linear regression model, we have so first of all, we need to understand that when we are talking about linear regression model, we basically want to understand the relationship between two or more than two variables in our data set. Okay. So whenever we have data set, we can identify the relationship between them. Now, there are two things like we have independent variables and dependent variables. Now, whenever we are talking about machine learning model, we are talking about one dependent variable and multiple independent variables. Okay. Now, dependent variable is a column in our data set that basically get influenced by other columns. Okay. Now, for example, if in our data set, let's discuss from here this particular example. For example, we're talking about some small scale business data and we are talking about its monthly sales and we are spending some money on advertising budgets, game quality scores, competing games, platform count. So basically we have a data file with all these columns where we have a column for sales, advertising budget. Our game is basically data is basically related to video games, game quality score, competing games, and platform count. Okay. Now, this particular data set have five different columns, and we know that the sales can be influenced by the quality of our games, and we also know that sales can be influenced by the advertisement budget, right? So what we are going to do is we are going to identify that what we can do to increase our sales. Okay. Now here our dependent variable is sales. Like sales depends on advertising budget, quality score, and all that stuff. Okay. And advertising budget and all the other columns are basically independent variables. Okay. Now what we are going to do is we are going to use them as independent variables and sales will be our dependent variable. We will model a relationship between them in the form of mathematical equation that helps us to understand what is going through in our data. What is the end goal of linear regression? The end goal of linear regression is, does independent variables affect the dependent variable? Like if we're talking in that particular examples, does advertising budget has effect on the sales or quality score have effect on the sales? If yes, what is the strength of relationship? Like how much effect we are getting by increasing the sales and something like that. What is the direction of relationship? So basically we can also identify that either this particular thing is helping us or it is making things worse for us, right? So this is the type of question. Hello.
Sorry.
Oh, it's okay. So this is the type of question that we can answer from here, right? Now we just discussed the scatter plot, right? Where we create the points for numeric columns. Like for example, if we have an X and we have an Y, so we created a scatter plot, we will see points like this, right? Now, what we will do whenever we are talking about linear regression is we're basically creating a line that pass through all these points. Okay. And what is the criteria for linear regression? So basically, it create this particular line based on the residual sum of square. Okay. And now, what we are going to do is let me open some. In this particular example, we have something like this, right? And we want to implement a linear regression on it. What will linear regression do? It will create some kind of line here, right? And how does it know the location of the line? So what basically it will do is it will find the distance from the line for all the points. Okay. And then create a residual sum of squares based on that. For example, if we're talking about this figure, we have all these points. What it will do is it will find this. Now this particular point, the black points are basically yi, right? And the point that where they touch the lines are basically yi dash. So basically these are actual predictions from the linear regression and this is the actual value of the particular point, right? So when we take a minus from there, we get a distance based on that. Okay. and this is what we call a residual. Like what will remain if we minus the actual value from the predicted value. Okay, so this line is basically based on the least residual sum of squares. So if we take the distance of all the points, we scale them and add them up. So basically this is what we call residual sum of squares. So we are trying to minimize it. Okay, so basically what linear regression do, it create line, it calculate this, it create new line, it calculate this again, and it will keep doing that until it gets a line with the least RSS. Understand? Do you have any question? Okay. Now, let's talk about the actual equation of linear regression. That's how actually linear regression equation looks like. Now here we have y dash. Y dash basically means the prediction generated by linear regression. Beta naught plus beta 1 multiplied by x1 plus beta 2 multiplied by x2. Okay, now this should be beta 2, not beta 1. Now let's talk about what is beta naught and beta 1. Now beta naught and beta 1, beta 2 are basically the coefficients, are basically the constants that represent the strength of relationship. Okay, and the sign basically, if they are positive, it means we have a positive relationship. It's negative, it means we have a negative relationship, and all that. Now in that particular case we have x and y, so that's why we are blending it with the x and y. We will discuss all of them in detail, like how we can calculate beta 1, beta naught, and all that stuff. The one thing that we need to understand is the here x1, x2 are going to be our independent variables, so we cannot add our dependent variable here. Like for example, if we're trying to talk about monthly sales and advertising budget, we cannot add sales as x1 or x2. Okay, and the dependent variable will always be a continuous variable. Like here we will always add a column that have numbers in it. We cannot add categorical column, or we cannot add any kind of variable with the text involved. Got it? But independent variables can be anything. It can be numbers, it can be categories as well. Now, when we implement a linear regression model, we get a table something like this. So when we will do this in Python, we will also get a table exactly something like this. Okay. Now, what here we have here estimates or coefficients. So basically, what are these when we generate the linear regression table? These are basically actual values that lies in our equation. Now, for example, we are talking about this particular model. Here, y is basically monthly sales, and x1 is basically advertising budget, x2 is basically game quality score, and all that. Now, beta naught is basically the intercept. So this particular value is basically the beta naught. This is beta 1, this is beta 2, beta 3, and beta 4. Okay. X1 is advertising budget, game quality score is something, it's x2, x3, and x4. Now, the first thing that we need to understand is what is beta naught. Okay. Beta naught is basically a baseline. Like if we want to see, if we don't invest on any kind of budget, we don't have game quality score or anything like that, what sales we are going to generate based on our data, right? So for example, in this particular equation, if I put beta x1 is equal to 0, like there are no sales, there is no game quality score, and all that zero, so what we will remain beta naught basically shows us that how many sales we are going to generate. Okay, now this number is basically trying to talk about that these are our baseline sales, and this number of sales happens when we don't invest on anything. Okay, we don't have quality score or anything like that. Now beta 1, beta 2, beta 3 represent the strength of each particular single independent variables, but before understanding that, we need to understand few things that we get in our output. We get standard errors, we get t-values, we get probability value. Now, probability value is basically a probability based on the t statistics. Okay. Now, this value should always be less than 0.05. If it's less than 0.05, there will some kind of stars appears. If it's one star, it means we are statistically significant but less significant. And 2 and 3 basically increase the significance. Now, what does significance tells us? If we have significance, if we have stars at the end, if our p-value is less than 0.05, it means this particular column is it has a relationship with our dependent variable. Like for example, here we're talking about four columns. Advertising budget. Advertising budget, if we take a look at that, there are no stars and the value is greater than 0.05. It should be less than 0.05, right? It means in that particular data or in that particular case, our budget, advertising budget is not doing much of the work. So our sales are not getting generated with our advertisement, and we have some kind of issue with our advertisement style or advertisement policy. Okay. And if we take a look at the game quality score is also not contributing as much as it should be in our data. But competing games has a p-value less than 0.05, and we are also getting 3 stars. This basically means it is statistically significant and strongly significant. So it means competing games is basically related with our monthly sales. Okay, and now this is just an example on a dummy data set, but when we're working on in the real world, we will see that our results makes a lot more sense. Okay. And platform count, like if we have more platforms, we will get more sales or something like that. And it's also statistically significant. Now, what we can assume from here is even though we have values in all of them, they are not zero, but they're only statistically significant when we have a p-value less than 0.05. If we have statistical significance, then we talk about their coefficients and what they tell us. Like if advertising budget is not even statistically significant, we cannot understand what that estimate basically means. Now let's talk about the theoretical stuff, that how this probability values are even getting generated. Now this is the equation of linear regression equation, simple. And this is the formulas for beta naught and beta 1. These are purely mathematical formulas that are basically automated in every softwares. Like in Python, in R, or whatever you're using, you don't need to do these. The Python will do it on its own for yourself, but you should understand the theory if it helps you in the interviews and something like that. Okay. Now here X is our independent variable. Like for example, if we're talking about beta 1, and advertising budget is basically X. So we are talking about advertising budget minus average advertising budget. And here yi is our monthly sales minus average monthly sales. So basically by adding all these, and summation basically means we find this for each row in our data set and we will take sum of them. Okay. In the same manner, we will take sum of all of them, and at the end of the day, we will get with a single number like this. Here we got 60. It's going to be a bit heavy on mathematics, but this is basically what's going on behind the table. We will calculate beta naught and beta 1 with these formulas. The standard errors that we get here are basically the continuation of the analysis. So basically, based on these beta naught and beta 1, we get the standard errors, and from standard errors, we get the t-value. Now, t-value is test statistics value. Test basically has a null hypothesis and alternate hypothesis. Null hypothesis basically says that there is no significant relationship between x and y. Like if we are talking about advertisement sales and this and monthly sales, t-value basically is a test that shows the significance between the relationship, and the probability is basically the probability of this particular t-value test statistics. So this t-test is basically giving us a probability value, and based on that probability value, we tells if there is a compelling relationship or not. Now, RSS is the same thing that we discussed earlier, residual sum of squares. Like we take the distance, we minus them, we square them and add them. TSS is total sum of squares. So basically we take the actual Y values, actual monthly sales values, and minus them from their means and take a square of them. Okay. And based on that, we create a new, based on these two things, we create a new thing that's called R square. R square is simply 1 minus divide RSS divided by TSS. Now, what does RSS tells us? Sorry, R square tells us. R square is basically a metric that tells us how much our independent variables are able to explain our dependent variable, or variation in our dependent variable. Now, let's see what does that even mean. Now, R square value should be around, it could be between 0 and 1. If R square is R square is close to 0, it means our independent variables are unable to understand anything in our dependent variables, and they cannot understand and they cannot explain any kind of variations in our dependent variable. Like there's no significant relationship. Okay. Now, if our R square is 1, it means it explains 100% of the stuff in monthly sales, right? But 1 is not logical. Like most of the time, we will not get 1. Most of the time, all the time, we will not get 1. Like it's an ideal scenario and it doesn't exist. Okay. We will get, if we are getting good results, we will get something like 0.8, 0.9, or something like that. In that particular case, we are getting 0.31. It means these independent variables are explaining 31% variation in monthly sales. So there are 69% of the monthly sales we cannot even explain with all these. So there must be some other instruments that are that are dealing with the sale. Like there is something else that affect the sales, and we need to understand what we are missing in our data set. Got it? Now, whenever we generate this particular table, what we are going to see is we're going to see something like that. We will have a p-value at the end. Now, this p-value is for the whole model. Like if it's greater than 0.05, we will not talk about this model. This is a bad model. If it's is less than 0.05, it means we should consider this model. Like in that particular case, it's much less. Okay. Now here the E basically is for scientific notation. Like if we are saying E minus 0.8, it basically means 10 raised to power minus 8. Okay. So we got the regression model results. We see the p-value. If it's less than 0.05, we say our model is good. Now let's talk about the R-square value. From R-square value, we see that we are able to explain this particular percentage in our dependent variable. Like we are talking about the sales. We want to see that what is basically driving the sales, and we don't know about 69% of the stuff that's driving the sales right now. But based on the 31%, we can see that competing games is statistically significant. Platform count is basically significant with monthly sales. Do you understand? Now let's start with the linear regression. Now, yesterday we discussed about the terms or the mathematical formulas for each of them. Today we are going to implement the linear regression on a real world data, and based on that we will find these results and we will try to interpret our findings. Now, here we already explained that in linear regression we try to find relationship between a dependent variable and one or more independent variables. When we're talking about only one dependent variable and one independent variable, we are basically talking about simple linear regression, or we call it a simple linear regression. Okay, its equation will be something like that: y is equal to beta naught plus beta 1x. Now, x is our independent variable and y is our dependent variable. But if we have more than one independent variable, it will be like multiple linear regression. And here we will have beta 2, beta 3, and up to beta n. Like how many? If we have 10, this will be beta 10xn. Now, linear regression model have some assumptions. Okay. And the first assumption that we're talking about here is linearity. Now, linearity means the our independent variable and dependent variable must have a linear relationship. Okay. And if you are unsure that how can I see that if they got linear relationship or not, you can just simply create a scatter plot, and with the creation of scatter plot, you will see that either the relationship is linear or not. Now, if we take a look at this particular plot, we cannot see any kind of relationship here. There is no linearity between them. But if we take a look at this plot, we can see a linear relationship here. Like with the increase of income, the house value is also increasing. So we are getting this kind of vertical line. This can be upward, downward, or in any direction. But the thing is, we can see a clear relationship here that if we are increasing the income, we are also increasing the house value. Either if it's go down, it doesn't mean that they don't have any relationship. Linear relationship is something like we can see a straight line in our data when we create a scatter plot. Understand? Okay. So before using linear regression model, we must be sure that our independent and dependent variables have a linear relationship. Independence. The observation in the data set must be independent of each other. So whenever we will run the model, what we will do is we will find their residuals and we will plot them. Okay, and they should not be correlated with any other independent variables in our data. Residuals, we talked about them in the last session, that when these are residual sum of squares. Okay, also our residuals should be normally distributed. Like if we find the residuals and we plot a histogram of them, we should see something like a bell-shaped curve. Okay. Now, this is not going to be the 100% perfect case. Like you see, all the conditions are met in our linear regression model because we are working with the real world data sets, and we might have to compromise on one of these whenever we're working on some real world problem. But if you are violating all of these, it means your model is not reliable and you should not be working on that particular model. No multicollinearity. So basically, no multicollinearity means there should not be high correlation between independent variables. We will talk about the correlation first, and then we will talk about the multicollinearity. And we have homogeneity. It means we should have constant variance and in the residuals across all the independent variables. We will discuss them with all these points when we are working on some data. Okay. In Python, we have two different packages to implement linear regression model. The first one is sklearn and the second one is statmodels.api. Now, we are already familiar with pandas, numpy, matplotlib, seaborn, and we use sklearn for scaling and for things like that, standardization and normalization in the data preprocessing session. So today we are going to also use sklearn, and from sklearn we will use standard scaler to standardize our variables. We will use model selection to basically split our dataset into training and testing datasets. Okay. And also we are using sklearn. In the sklearn package contains some datasets, so we are fetching data from here and we are going to use it. We will also be importing linear model, sklearn.linear model, linear regression model, because we are going to use it. That's why we needed it. We will also use matrix. Matrix are basically terms like mean absolute error, root mean square error. These are error metrics that we use to compare different models. Statmodels.api is another package that can be used for linear regression model. Now these are some basic default styling style, but you can ignore it if you don't like to add these. So we use fetch California housing. Basically, we are fetching a dataset from the sklearn package. Okay, and we are giving it a name df. In the sklearn, we have names and the data separately, and the target variable or the dependent variable also separately. So we will combine all three of these into a single data frame. So first we are combining the data with the names, and then we are adding our target variable into our data with a new name, like median house value. Since we have a data frame, we can just see it, that how it looks like. This is the data frame related to housing, and we have different like average number of rooms, average bedrooms, average population, and all these terms in our data frame. and our main object is to find the median housing value. No, there are small numbers, but they can be in millions, like 4.5 to millions, 3.5 million, and something like that. Okay. So since it's a continuous variables, we can use linear regression here, right? And all these columns are also in numeric form, so we are good to go. Now, this session or the upcoming sessions will be like a revision of all the topics that we did in data cleaning and data visualization. So we will use both of terms from both of those sessions. Okay, so now we will start with the simple function like df.info. It will show us that in our data set there are 20,640 rows and all of the rows are non-null. It means there are no missing values in our data set. Okay. And all of the columns are in the float 64. Float 64 basically means in decimals, and this is exactly what we are looking at. So it means our data set is pretty clean and we don't need any kind of cleaning here. But we have a problem of scale, like house age has such a higher numbers, and another columns like average bedrooms have quite lower numbers, so we need to scale them up to a same standard. Mm. And we will use standard scaler here. Apart from df.info, we can use df.describe to see the terms like minimum, minimum, maximum, median, and different percentiles. Now we know that we can see that how many missing values we got here, but if we want exclusive for the missing values, we can also use df dot is null. So basically the missing values in that particular data frame and sum them up. If we have some missing values in column, it will sum them up and it will show them in front of it. But since we are good to go, so there are no missing values here. Now we will go with the visualizations. We will visualize our main column, a target column. Now why we are doing that? Because we have an assumption that the target variable should look like normally distributed data. For this, we are using SNS or Seaborn package, and we're using function histogram. All we need to do is provide a our target variable here and the number of bins. We can adjust that if we want to increase the size of the bar on the x-axis. We are using KDE is equal to true to basically get this blue line over here. Apart from that, we are using just title customization, X label customization, and Y label customization. Now, till now, we just explored our data set, and now we are going to talk about correlation. Now, let's discuss the correlation first, and then we will discuss it in our scenario. Now, correlation value of any two variables, any two columns, we find our correlation when we have independent variable, numeric independent variables, okay? And what correlation tells us is that how much these two particular columns are similar, okay? Maximum value for correlation is 1 and minimum value for correlation is -1. So whenever we have correlation values between two columns, let's say close to 1, we say they are highly likely that they're similar in nature. Like if one increases, the other one also increases, and same goes on in the negative sense. And the least value that we can get is -1. -1 means they do have strong relationship, but with the increase of one, the other one decreases. And if our correlation value is 0, it means there is no relationship between these particular columns. Like for example, finding correlation is quite simple. All you need to do is just use df dot core. Now this is a function that finds the correlation, and you can save it as a matrix here. We're using correlation matrix, and you can give it any name. And a better plot, a better approach is to plot the matrix so you can clearly visualize it based on the colors. For this, we can use SNS.heatmap. Heatmap basically convert the matrix into a proper plot, and we say not is equal to true. So basically add the values on each block. We can give it a color, cool, warm. We can have different options here for the CMap, but here we are choosing cool, warm, and based on that, basically it will give it blue color when it's close to -1, and a red color it's going to when it's close to +1. And here we're using format is equal to 0.2. It means we only want two decimal places for each number. So we are basically rounding every number to the two decimal places. Again, some minor title customization. So basically when we plot this, all we have, you can see is we have the column, our dataset contains some columns, right? And each column name will be presented on both axes, x-axis and y-axis. And if we want to see the correlation between any of these two variables, for example, I want to see the correlation of average bedroom with average room, right? So we will just correspond to the value that is in front of average bedroom and average room, 0.85. Now we are getting a much higher correlation here. And this is obvious that if we are increasing the number of rooms, in the property, it means there will be more bedrooms, right? Okay. Now, if there is no relationship between these two, any of these two things, we will get numbers like 0.00 or 0.01 or something like that. 0.07, they are very close to zero. So these columns don't have specific relationship. For example, if we see that this is 0.07, here we are talking about average bedrooms and latitude. Now, the latitude basically refers to the location of property, and location of property has nothing to do with the average number of bedrooms, right? Longitude, latitudes are basically the values that we see on Google Maps or something like that when we're talking about some location. So this is the correlation matrix. And when we are working on any kind of, and when we are working on linear regression model or any other different machine learning models, we assume that our independent variables should not have higher correlationships. If two variables have a correlation of 1, it means they're representing the same thing. So we don't need to add both of them into model. If we add two highly correlated columns in our model, it will create problems or it will introduce a bias in our model. So this will make the results unreliable. Now, this part, data pre-processing, we discussed it earlier, we standardize the columns. But the here for this particular thing or for any machine learning model, the one extra step that we do in pre-processing is we split our data set. Okay. Now, before splitting our data set, we first need two different data sets. First, for independent variables, we call it X. You can call it anything. If I prefer X, so it's totally up to us, right? Now, these are independent variables. Now, what we are doing here, we are just removing our dependent variable from our data, right? We basically are trying to predict the house value, median house value, and we don't want it in our independent variables, right? And this particular thing goes to dependent variable. So this is our dependent variable and rest of the columns are independent variables, right? Now, what we're going to do is we're going to split our data set into 4 sections. X-train, X-test, Y-train, Y-test. Now, we have two data set till now, X and Y, right? What X do? X basically is independent variables. We divide it into two more sections for training set, for testing set, right? And in the same thing we do with the Y, we divide it for training set and for testing set. Now, why do we do that? We will discuss it later on. Now, to do so, we have a function in sklearn package, train test split. Now, what it will do is we just give it both X and Y, and we will give it the test size. Okay. Now, test size basically means how much data should be in the training set and how much data should be in the testing set. We give it a value of 0.2. It basically means 20% data goes to test data, and 80% data goes to training data. If we want something like 70-30, we can just change it to 0.3. Okay. Now, testing size will be 30% of the whole data, and how it will split it will split it randomly, right? It takes all the data, like we have 1,000 rows, it takes 30% of the data randomly, like random 300 rows from thousands, and it will add them into the testing set. And the rest of the rows will be go to the training set. Now, there is a parameter random state. So basically we assign that random state is equal to something like this. You can give it any number here. So the main purpose of doing that is, so whenever we rerun our code, every time we get the same split, we get the same data set, right? Like you are writing some report and you split our data set and you wrote the whole report based on your analysis, but you didn't specify the random state. And next time someone run the code, the new random data set has been generated and your whole results are messed up. Okay, so that's why whenever we're working with some randomness, we always take care about the random state. Got it?
Yes.
Perfect. Now, that's how basically a linear regression model output looks like. Now let me make it a little bit more. We are trying to understand that. We are trying to understand that how these particular beta values influence our line, right? Suppose we are talking about, we are taking an example where we are trying to find the relationship between house size and price. Okay, and we want to fit the line that follows along so we can have a relationship. Now, since there are only two things like house size and price, how our equation will look like? Sorry. Okay. So how this equation will look like? So basically, we're trying to predict the sales is equal to beta naught plus beta 1. And with beta 1, we will have house size, right? Now, we are trying to find this particular equation for this example. Now, let's see how beta naught influence and how beta 1 influence the line, the regression line. I basically created this particular dashboard just for you so we can understand the influence of beta naught and beta 1. Okay. Now, beta 1 is also known as intercept. Okay. Or we can say what will be the value of our dependent variable when this particular term is 0. Like if we got nothing here, what will be its value? Now, this intercept basically means beta naught, and this slope basically means beta 1 in this case. Let's make the slope 0 and see what basically beta naught influence for. Okay, now this is the intercept. If I move around here, I will see that it will just move upward or downward our line, right? It doesn't introduce any angle to our line. Like we have this, we need to fit data something like that. We need to optimize beta naught and beta 1. Now beta 1 will influence that where the line should start. Okay, and the sorry beta naught and beta 1 will influence the direction. Okay, now if we are trying to fit something like that, this will be the most close to best fit, but we can just click here and it will gives us that at this particular point we will have the optimum value beta naught and beta 1. Now this is just practical understanding that what basically beta naught and beta 1 doing behind the hood. Okay, and this is basically most of the thing we don't do that manually. Python do that on its own, but for the better understanding you should know that. Do you have any question?
Yes.
Okay, if you have any question, please feel free to ask. Okay,
Yes.
and we just give the data to Python and we just say sm dot ols. Ols basically means ordinary least square. Okay, it's the different name for linear regression. We just give it training data for our dependent variable, training data for our independent variables, and we say dot fit. It will just fit the model and it will give us this particular summary. No, what Python will do is Python give us the coefficient values, like what optimum values will be that make the lines on exact on the point. What should be beta naught, what should be beta 1. Okay. And with each value, we will get standard errors. And for each standard value, we get test statistics, and based on that, we will get a probability value. Now, the main thing that we should be worried about is the p-value. It should always be less than 0.05. Okay. If it's less than 0.05, it means our variable is significant, like it has a relationship with our dependent variable, right? Now I'm going to bit talk about mathematics here. It will be a bit mathematics heavy, but I think it's worth it to understand what goes behind it. Now let's talk about the p-values first. If it's less than 0.05, we say our dependent variable is significant. Independent variable is significant. Now, what does that means? That means what relationship that we're trying to model. Like, for example, advertising budget. In this particular example, we're trying to model relationship of sales with budget and all their different scores. Now, if this particular column is statistically significant, it means that competing games have a relationship with sales, right? I think we discussed that in the previous session. Did we?
No, I don't remember.
Okay, no problem. Now, we have this equations, mathematical equation, right? By using these two formulas, we formulate beta naught and beta 1. Okay. Now, in these formulas, x basically are independent variables, like each point in the data. Mean of x basically the overall average of that column. Y is our dependent variable, and mean of y basically the whole thing. Like if we go back to our data set, for example, in this thing, if we're talking about beta naught, what we basically xi. Now beta 1 is basically related to some independent variable in our data set, right? Like in this equation, we have beta 1 associated with some independent variables. For example, in this particular case, we are talking about advertising budget and sale, right? And now beta 1 will be the whole data related associated with that independent variable. And the mean of that column basically will be the average value, that if we calculate the average, what it will be, right? And y is our dependent variable. In the same manner, y, the whole column minus its mean value. So we will get two different columns, right? And we will take sum of them. This is basically summation. So we'll multiply them first and then take the sum of all of the values. So we'll get a number. And we will do similar, but with the x only in the divider. Do you understand? Do you have any question? Do
No.
you have any question? Feel free to ask. If it's a bit overwhelming, like what going on, it's totally fine. Like it's a bit mathematics heavy, so I can understand. Okay.
Mm.
Okay. Now, so similar, we have formula for beta naught, and based on these beta 1 and beta naught, we get standard errors with this mathematical formula. So you really don't need to learn all these formulas. But if you are preparing for some interview or some public speaking or demo, then you should know that. We have a t-test or a t-value in our table, like this one. Like this one, we have a t-value, right? And what basically this is basically a statistical test that has two hypotheses: null hypothesis and alternate hypothesis. Now, null hypothesis is there is no significant relationship between x and y. Like if we are talking about this table, x1, we are talking about x1, our first independent variable, with the dependent variable median house value. Okay. And let's put it here. So either it has no relationship with dependent variables or it got a relationship with dependent variable, right? Now, how can we verify that t-value, or we can verify that test? We can verify that t-test based on the p-value. It should be less than 0.05. If it's less than 0.05, we will go with the alternate hypothesis that there is statistical significant relationship with dependent variable. Now, when we have the table here, but we will start with the p-values first. Like we look at the p-values. Now here we have 0.699. It's greater than 0.05, right? So this particular column, x5, or the fifth column in our independent variables, is basically have no relationship with the dependent variables. So this particular column should not be should it has no relationship with it is not influencing our dependent variable. Like for example, if we're talking about the house value, and this is something the neighborhood or something like that, so it has no relationship with the actual price of the house. Now we go through this p-values. We know if it's less than 0.05, this particular variable is important. Now what we will do next is we will take a look at the coefficients, right? If we have a bigger coefficient, it means it has more strong relationship with our dependent variables, right? And a smaller coefficient basically means we do have a relationship because we already validated the p-value, but the influence of this particular column is less on the sales or any dependent variable, right? Now, basically, this t-value is helping us to find the p-value. So in general, these values don't make any meaningful full impact, but the t-value generated from is this basically helps us a lot to interpret our results. And now let's talk about the confidence interval. Now, this is basically a confidence interval that we are 95% sure that the value of x1, this coefficient, should be between these two values. It can be as less as 0.83, and it can go up to 0.87. And most of the time, it will remain between these two values. Got it?
Yes.
Okay. Now, we created a model, and based on that model, we generated this particular output. We know how we can check the influence of each column, each independent variable. We can now tell that either it's significant, we can tell how much it is influencing the dependent variables. Now, there we also have negatives. Now, basically, negative means increase in this thing, increase in this independent variable basically cause a negative influence on our dependent variables. Like, for example, if in our data set, we are talking about the x3, now this is x1, x2, x3, average rooms, right? So if average rooms have a negative influence, for example, now what does it mean? It means if there are more rooms, it will reduce the price. Got it? Now, this might not make sense in that particular example, but this is actually what a negative coefficient means. Got it?
Yes.
Now, in that particular example, now another thing that we should understand is R square value. Now, everybody knows that the more rooms if we have more number of rooms, we will have higher price, right? But we are getting these results on this particular data. Now, there are things that we should understand why. The first thing that we need to understand is we need to treat our data more better. Okay? Like for example, in this particular example, I just wanted all the columns, so that's why I did all of them, right? But if we take a look at our data set, latitude, longitude, now these should not be included, okay? Because they tells us about the location of the map, location on the map, regardless of the neighborhood, like it's in premium neighborhood, it's not in premium neighborhood. We don't get all these with these two. So whenever we're working on linear regression, we don't want to include them. And we also see in the correlation matrix that every bedroom and every rooms have a higher correlation. So if we are trying to make the perfect model, we will not include those. We will not include both of them. We will include only one from them, right?
Yeah.
So, so these are basically the things that I left it deliberately in this. So basically, when you are working on your own, so this is kind of little assignment to you that you should just check these things, remove these things, and see that how much it influenced my model, right? So when you do that, it will start to make sense. Got it? For the starting point, I just took all the columns. Try it on your own, and if it doesn't work for you, you can check, you can ask me back, and I will do the coding for you. Okay?
Okay.
Now, in Python, we have two different packages. We have sklearn or scikit-learn. Sklearn basically provides us with the linear regression model. We have statmodels.api that also provide us with the linear regression model. Okay, now the table we generated is with statmodels.api, but we can do the same thing with sklearn as well. Now here we are using sm.ols. Sm basically means we are using statmodel.api. Now if we want to do with our standard sklearn, all we need to do is just use the linear regression function. And with this function, we will just fit and we will provide the training data and training y data, independent and dependent both. Got it?
Yes.
Okay. Now, one thing we need to understand here, we know that we have x and y, right? And x means dependent variables, y means independent variables, right? Sorry, x means independent variable and y means dependent variable. Okay. When we are trying to fit the model, we give it both the dependent and independent, both. We give it full data, right? It train the model based on that. It will gives us this particular table based on that, or we can get coefficients like this for each of them, right? Now, when we use SM stat models API, it's giving us x1, x2, x3. So it is basically giving us random names. But when we use sklearn, it gives us proper names that for this particular column, we have this coefficient, for this column, we have this coefficients and this. So that's why sklearn is more used in industry standards. Do you have any question till now?
Oh,
Are everything making sense, right?
yes.
Okay, perfect. Now we train the model, we give it independent data, independent columns, we give it dependent columns. Model fit, we have our coefficients. Okay, now we want to evaluate our model that either these are good or bad. Now what we will do is we will predict our test set. Now we have two different types of data, independent columns, dependent columns. We created two more based on both of these, test set and training set. Now, initially we used training data to train our model, and now we will use test data to test how our model is performing, right? So we will use the name of the model, the that we just created. Like in here, we just created this particular thing, linear regression is equal to linear regression, and fit the model, it will automatically save the model in this particular name that we gave us, right? And we can use that name to get the predictions. And in prediction, we are specifying that we are giving you independent variables from the test set and you predict the values. So now these values that it will, we didn't provided it with the y test or the test values for the dependent column, right? So basically we are trying to generate the predictions and we will compare these prediction with the actual values. And based on that, we will see that how much our model is accurate. So if we're talking about this on this particular graph, what basically we're going to do is we're generating predictions, right? For example, let me take a screenshot. Now that's our data points, right? What we did is we created two sets. For example, we created, for example, this is our training set, right? And this is our test set. So what we did is we provided the values associated with each point on the x-axis and on the y-axis to the model. And based on these values, it draw this particular line, that this particular line is the closest to all the points. We extended this line till here, okay? And why do we do that? Because we are trying to test that how much this line is close to all the points, right? Now here we know that we gave it the values for x and y, and it generated this particular line. But we want to see that if we don't have y values and we want to predict these values, then how much our model will work. So what we are going to do here is we are only giving it independent values, like the only for the values of x, okay? And this is basically generate prediction. Now what is prediction? Basically this blue lines are giving us the prediction. Like for example, if we want to say that this particular value is something like 78 or 79, sorry. And what we are going to do here is we have the actual value. We know its value on the y will be something like 25, right? But we want to see that how much our model will predict or how much the regression line is far away from this. And this is the actual value will be like something like 25, and this is basically something like 22. Okay, no, this is the whole point. We don't know about the y values or the sales values or anything that we are trying to predict. The regression line, how far it will be away from that particular point. Okay. Now, for example, this x is marketing budget and this y is number of sales. So if you are saying that we know that when we have 50 marketing budget, our sales are 16. But if I increase it to 100, what our sales will look like? So this is what regression model tells us. Now what we did is we split our data set into training testing. We train our model, basically this particular line. And based on that model, we generated predictions. So we have all these points, we call it actual values, and we have this particular line, and from these values we call it predictions. Now let's talk about how we will assess that either our model is good or bad. Now there are error terms or evaluation metrics, like there are different kind of errors, mean absolute error, mean square error, to see that how our model is performing. And now to test that, we have something like called MSE. Okay, we have basically different error metrics, mean absolute error, mean standard errors, and things like that, right? So we will start with MSE first. Now MSE is an error term, so basically that tells us how much our model is good or bad. Okay, and now here yi basically means the predicted values that we predicted. Like in here, the values on this particular line, right? And yi basically means actual value, these points that are away from the line. So what we do is we minus predicted values minus actual values. We takes care of the values and we will sum that for all the points, right? So we will find the difference between this point and this point, this point and this point, all the points, we take care of them, and we will sum up and get a single number, right? That tells us about that, and we divide it with n basically means total number of points. Like if there are 10 points, so how much average error we are getting, so we get a single number. Now this number basically represent MSE or mean square error. Okay, and mean basically means average, square basically we take because we take the square of it, and E basically means error. So basically predicted value minus actual value here. And now what this tells us that how good or bad our model is. Now the thing is we just got a number. Like for example, we get MSE of 10. How do we know it's good or bad? Now what in programming we do, we go through different models and we choose the best one with the minimum MSE. So MSE value itself don't tell you anything, but it helps you to compare between different models. Okay, and based on that, you know that what model is giving us the least error, and that least error basically helps us to identify the best model. Do you understand?
Yes.
Okay, now the main question that is left right now is that we know we fit a line, we know we have beta naught, beta 1 values, we know how to calculate them. But the main thing is what algorithm or what magic or what mathematics Python do to get to the best line, right? It can make mistakes. We can have a line here or something like here. So how does basically it does that? Now this is the simplest example where we have one independent and one dependent variables, but we have like 5 to 10 different variables. So it will be a high dimensional figure if we try to make it, right? So how does Python get to this precise line? Now, what does Python do is Python basically, in Python, we basically use an algorithm that's called gradient descent. Okay. Now, what gradient descent do is we have a model, we get W naught, W1, W2, basically beta naught, beta 1, beta 2, right? And we calculated the error, we get something like that, right? What basically we will do is we use the gradient formula. This is the gradient formula. Okay. J is basically here is MSE, the mean square error, and WI basically means the first weight, like the beta naught, beta 1, beta 2. For J is equal to 0, it will be like beta naught, then beta 1, beta 2. So we will do this step individually for each coefficient or each independent variable. So what we are trying to do here is we are create using a derivative. Okay, so basically derivative basically means the change. Okay, so if we change the value of W or this particular weight or this particular coefficient, how much J will change. Okay, so based on this formula, we it gets new values. Like at first we give it a random beta naught and beta 1 value, right? We give it random beta naught and beta 1 value, the lines instead of here, it gets something like here. Then we will put these values in these formulas and it will optimize it, right? So these derivatives basically helps us to identify the optimum beta naught or optimum beta 1, 2, 3, and all the different coefficients, right? So this is called gradient descent. Now here, W naught is basically beta naught, the actual random value that we took at the first step. But what it will do is it will take a alpha, use it to get an optimized W value that will basically reduce the error. And alpha here is basically called a learning rate. So it's a value between 0 and 1. Like if we see that the line is far away from the point, so we need a bigger jump, we choose a higher number for the learning rate like 0.5 or 0.6. If we need small modification, we take like 0.1 or 0.2. Do you understand? So basically what we are trying to do here in simple words, we are trying to get the perfect W, perfect beta naught and beta 1. And that basically leads us to the perfect line that is closest to all the points. Got it? Okay, so this was ton of mathematics and ton of formulas. So let's talk about in the simplest form, if we want to say, what is linear regression? In a model that helps us to find the relationship of one or many columns in data to a single column, right? And we know that single column should be continuous column, or it should be numeric column with numbers. It should not have categories. That's what we call dependent variable. We have a equation like this. When we train the model, we get the values for beta naught, beta 1, beta 2. And all these beta values have associated p-value. This one, based on that value, we tell if this particular column have a relationship or not, right? And we also know the direction of relationship, like if it's positive, it means with the increase of this column, our dependent variable also increase. With increase of this column, our dependent variable decreases because we have minus sign here, right? Also in linear regression model, we have R square value, like this one, its value will always be between 0 and 1. If it's 0, it means our model is bad. If it's close to 1, it means our model is good. Like here, it's 0.6. Basically, it means we are able to explain 61% of the variance in our dependent variables, like housing value, right? So how does it increase? It increase if we add more factors or more columns in our model that have relationship with our dependent variables. Got it? Now, there are a lot of different terms, like if, for example, we have F statistics. F statistics is also basically a different test, statistical test that tells us about how good our model is. Like now, again, in the case of T, we deal with the p-value. Similarly, for F statistics, we have associated probability value. P-value basically means probability value. Okay, it should also be less than 0.05, and if it's less, it means overall our model is good. Okay, and no, that's what we do in linear regression model. So this is another example. We have insurance data set. We just loaded the data set in our environment. In this particular data set, we have columns where we have text instead of numbers. So what we did is we use get dummies. Get dummies basically is related to one hot encoding that we discussed while pre-processing, like how we convert the text columns into numbers and then use it into models. Again, in the same way, we split the data set into training and testing. Again, we converted into 4 columns. We standardize it. We use the regression model. We get the predicted values on the test set. So basically 90% of the time code will remain the same. All you have to do is you have to know that what you're trying to do, right? You have to know what is your dependent variable. You have to know what is your independent variables and what you're basically going to do with them. So I will share these links. I will share the videos, and I will share also this book, this notebook. In the next session,
Okay.
we will start with the logistic regression.